Alrighty, in this video we're going over the solutions to the practice test for applications of differentiation. So make sure you got this, make sure you got your formula sheet, make sure you got your calculator, make sure you've tried the full test under test conditions before looking at the answers as well. First question is shape and inflection. It's a sign diagram question. So here f dash of x is going to be minus 4x cubed plus 4x. There we go. Now if you want, you can take out common factors and then you would know what goes on your sign diagram. So in our case, you'd get x is 0, x is 1, and x is minus 1. Just like that. Because x squared take 1 gives you that bit, and x is 0 gives you that bit. But realistically, what I'm expecting a lot of people to do is just sort of cheese the sign diagram by looking at the graph. And you have calculators, so you might as well use them. So we got minus x to the power of 4 plus 2x squared plus 1. There it is. So we're going to draw that function, go V window, back to standard. That should help. There we go. Lovely. And we can see that we do have maxes and mins at, looks to be 0 for that minimum. And if I go max, it's minus 1 and 1. It went up, down, and that is f dash of x. Find f dash dash of x. So f dash dash of x is going to be minus 12x squared plus 4. Now again, you can sort of play this game to solve when it equals 0. So you would get 12x squared equals 4. Therefore, x squared is 4 over 12 or 1 over 3. Therefore, x is plus or minus 1 over root 3. Now, if you did it on your calculator, which is still fine, you can just get approximates for that. So 1 over root 3. Actually, doing this on the calculator can be a bit tricky to find inflection points, so you sort of do have to solve this one by hand. So it's about 0.577. Now on our sign diagrams, although it is a different question, I am still going to try and line these up. So kind of there, I'm going to have minus 1 over root 3, and then kind of there, I'm going to have 1 over root 3, just like that. That's x and f dash dash of x. On the graph, let's go back to that. So it looks like we're concave down, then up, then down. Because it's sad, then happy, then sad. Classify all stationary points. So we have minus 1, we have 0, and we have 1. Let's get the y values for all those. So we got the function graphed. I might just go g solve max to get those two maxes. You get minus 1, 2, and 1, 2. Say local max. So is this one. And the other one, shift G solve min, 0, 1. It's a local min. Find and classify all inflection points. So we have one which is at 1 over root 3, and then we can trace that value. So shift trace 1 over root 3. Now I'm just going to be very careful and just put that 3 in brackets. It should work either way, but so 1.555555555 or 1.56 to 3 significant figures. It's a non-stationary point of inflection. And minus 1 over root 3. And I think that should have the same y coordinate, but let's just check. Shift trace. And I'm going to type in minus 1 over root 3. Yeah, same thing. 1.56, and this is also a non-stationary point of inflection. You could get fractions for that as well. The 1.5s, you could just hit S to D after typing in a bunch. So if you did want the exact versions, not that I'm asking for it, just do that for a little while and then hit S to D and it should give you 14 over 9. For what values of x is f of x concave up. So if we look at our graph here, well actually we don't even need to because we've got it on our sign diagram. In between minus 1 over root 3 and 1 over root 3. So that's pretty much everything we need to do for that question. Okay. Kinematics. So let's first of all get this graphed. So it's going to be x to the power of 3. Take 9x squared plus 15x. Take 5. We draw that. Now, on my V window, I do want to start at 0 for the x value. Always start at 0 for kinematics problems, very important. And I'm missing a bit of y down here. So minus 10 might not be low enough. Let's try minus 30 and we'll see how we go. That's a bit better. Just barely scraping the bottom of that, I might actually go minus 35. Just for a really good view of this thing. There it is. Find expressions for velocity and acceleration, drawing sign diagrams of each. So s of t is going to be t cubed take 9t squared plus 15t take 5. The velocity is the next derivative down. That's going to be 3t squared take 18t plus 15. And then acceleration is going to be the next one down after that. So that's 6t take 18. Now, for what to put on the sign diagrams, there's a couple ways to do this. So let's just get our sign diagrams mapped out first of all. So that top one will be velocity, and then that next one down will be acceleration. Now, 6t take 18. There we go. So basically, you could solve it to get 6t equals 18 and t equals 3. So that's going to go on that sign diagram. If we go 1, 2, 3. The velocity sign diagram, there's a couple ways to do it. So you could go g solve max, there's 1, and you can go g solve min, there's another one at minus 30. Minus 30 is a y value. There's one at 5. So there's 1, 3, 4, 5, just like that. The other way that you can do it, if you're ever in a pinch, is go to equation mode and actually polysolve that velocity equation. You know, or we could just solve the quadratic by hand. 3 minus 18 and 15. Just like that. Solve that. 5 and 1. Coming back to our graph, let's see what that looks like. So the graph there looks like that. It goes up, down, up for the velocity one. And it's sad, then happy. So it goes minus and plus. Or concave down, then concave up. All right. We need the initial conditions. So s of 0. If you plug in 0 for the t value here, basically everything goes away except for that minus 5. And I believe we're in meters for this question. Let me just make sure. Yep. V of 0. Same thing. All the t's go away, so you just get 15 meters per second. Do be careful about this because if it's a polynomial, it all goes away. But not all functions will just have it always go away. So you do actually have to plug in t equals 0 to make sure. We are meters and seconds, so that's really good. Okay, so the particle starts 5 meters left of the origin with velocity 15 meters per second towards the right. And it's worth mentioning that it's slowing down because the speed and velocity, acceleration and velocity are pointing different ways. Down with acceleration 18 meters per second left. Just like that. Okay. Find the times and positions of the object when it turns around. So t equals 1 and t equals 5. They're on our sign diagram just there. When t equals 1, so that was the maximum there, y is 2. So we can say that s of 1 is 2 meters. And then when t equals 5, s of 5 is minus 30. Cool. All right, so it turns around at 1 second and it is 2 meters right of the origin. And it turns around at 5 seconds and that's when it's 30 meters left of the origin. Beautiful. Draw a motion diagram for the object. So with this motion diagram, basically just looks a little bit like a sine diagram, but it's not time that you're measuring, it's actually the position of the thing on there. So it starts, let me just remind myself, trace of 0. So it starts at -5. We need to make sure that we at least go down to that minimum. So left, we need to go down to -30. So what I might do is I might put 0 a little bit off center here. I go -5, -10, -15, -20, -25, -30. Now, let's see what's it doing. So it starts at -5, it then goes to the right until we hit that maximum value of 2. So it's probably going to start here, go up to 2, turn back around, go all the way back to -30, and turn back around again. We need to label these times, so t equals 0 there, t equals 1 there, t equals 5 there. For what time intervals is the speed decreasing? So that's when acceleration and velocity are pulling different ways. So we probably should put 0 on those sine diagrams. Between 0 and 1, we've got plus and minus. So 0 is less than t is less than 1. And we've also got it being minus and plus between 3 and 5. That's where they're different. And 3 is less than t is less than 5. So that's how we answer that question there. All right, we got this question here about the blue screen of death on the computers and an IT repair business having people surge into the shops, so to speak. So what we're going to do here is we're going to graph this function and see what we get. 100t e to the minus t. So we're going to go 100 and use x, and then it's going to be e to the power of minus x. There we go. Draw that. So it's a lovely surge graph. Since this is a real world, time is not going to go negative, and we won't have people going negative. This is people entering the shops. I guess in theory you could have people leaving considered negative, but this graph doesn't really track who's leaving, it only tracks who's entering the shops. Cool, so we just need a bit more in our y, we're just missing the top. Maybe let's go 50, see if that gets it. This is called a surge function because it sort of has that initial surge and then tapers off towards the end. And you can imagine that this would be the shape in the real world. So 9 AM, when everyone wakes up and their computers are broken, they're all going to run into the shop, try and get them fixed when the shop opens. Some people are still driving there and whatnot, so they might not get there till 10. 10 is the peak and then it sort of goes away. So usually what I like to do is I like to trace a few values just to make sure. So trace at 1, I got 36. So I should put in this point here. Now you don't necessarily need to do this. It just helps to make the graph look a little bit nicer. You don't need to do every point, just maybe like trace, like 3 could be a good one, 14. So sitting about there, something like that. And maybe I'll just trace at 5 just to get another point in there. And it looks like 3.368, so probably sitting much lower at 5. So the graph is going to look like this. And then sort of leveling off there. We can label it. B of t is 100t e to the minus t, just like that. Cool. So there it is. Find B2. All right, so you've got to go trace into 27.0 or 27.1. So people per hour. So at now 2, since the time starts at 9 AM, this will be at 11 AM. There are approximately 27.1 people per hour entering the shop. Now, we got to be really, really careful about this question. We're used to graphing on the y-axis like an amount of people. We're actually graphing the rate on the y-axis. So this graph is almost like the derivative of the total number of people in the shop. So it's just a bit funky with the interpretations. B dash of 2. So when we did this, we got minus 13.53. Now, if you didn't have that number showing, you got to go Shift Menu and turn derivative on. That'll do it for you. So when you do that, Shift Trace to minus 13.53. B dash of 2 is minus 13.53. Now, this is going to be a really weird unit. People per hour, right? So the speed of people entering is decreasing. It's a very weird unit, but that's the units. So at 11 a.m., the average people per hour entering the shop is decreasing. At 13.53 people per hour. Very weird unit there. So basically it is getting less busy. Okay. So really what we've just worked out is sort of the slope at 2, and you can see that it's sloping down there, so it's getting less busy. Find the busiest time for the store and the rate of people entering per hour at that time. Now, usually in these questions, when I ask for rate, I mean the derivative, but since we're already graphing the rate, it's a bit different. Busiest time for the store, Shift G solve max. There it is, 136.8. All right, so that is the max. Busiest time is T equals 1. So that is 10 a.m. and we've got 36.8 people per hour entering. If the store has over 25 people per hour entering for any longer than 2 hours, their lines get too long and they need to call in their emergency staff. Look, to be honest, if you had this issue, I probably would be calling them in before the store opens, but let's see how we go. Over 25 people, so G solve xcal and 25. So T equals 0.35. Let me check the rounding on that. 7. So through 2, T roughly equals 2.153. So we can say that this is B is greater than or equal to 25, 4, and then it's those times. Total time is roughly 2.153 take to 0.357, and we can work out what that is. $1.796 hours. So no, don't need to call them. Now, I really want to point out this question is a pretty unusual rates of change question because we're graphing the derivative. I wanted to point it out because I want you to get used to interpreting these in different contexts, but do try some of the more normal questions on this where you're graphing just the quantity on the y-axis because you want to practice both types. All right, next up we got a wonderful conjecture question. Now this is about tangents, so if this equation of the tangent is not on your cheat sheet already, make sure it goes on there. A is the x value we're dealing with. F of A would be f of 1, so that is e to the minus 2 lots of 1, which is e to the minus 2. The derivative is minus 2 e to the minus 2x, so f dash of A is f dash of 1, which is minus 2 e to the minus 2 lots of 1, which is minus 2 e to the minus 2. Plug all these numbers in, we're going to get minus 2 e to the minus 2 out the front, x take 1 there, and then e to the minus 2 there. We can then pull out a common factor of e to the minus 2, and we'll be left with this stuff. And then this will just be factorizing. Since it's a show that question, I like to sort of explain what we're doing, and then I'll draw this little arrow out there. Then we can expand inside the brackets. So you're going to get minus 2x plus 2 plus 1. Now this should start looking familiar to our show that bit up the top there. We can then just use index laws. So minus 2x plus 3 will stay on the top and e squared will go on the bottom because that's a negative power there. Index laws. And since it's a show that question, we like to write as required at the end. We've got a triangle there that this tangent makes. So we've got to find the area of that triangle. So that blue line there is a tangent. It makes that triangle in yellow there. We have to find the area. Now I've given you a hint there to find your x and y intercept. So Q is the y-intercept. And P is the x-intercept. Now to find a y-intercept, you just set x equal to 0. So our function was this from before, minus 2x plus 3 all over e squared. And we just got to set x equal to 0 on that. Minus 2 lots of 0 plus 3 all over e squared, which is 3 over e squared. To get our x-intercept, you have to set y equal to 0. So again, it was y is minus 2x plus 3 over e squared. You're going to get 0 is minus 2x plus 3 all over e squared. Now, if you remember this about fractions, just the top of the fraction has to be 0 for this to happen. Alternatively, you can just times both sides by e squared, and you'll get 0 e squared on the left, which goes away. So 2x is 3, therefore x is 3 over 2. Now this should be good news because we're saying that x here is 3 over 2, and it certainly looks to be at 1.5 on that graph there. And the y value we've claimed is 3 over e squared, and if you work that out approximately, you get 0.406, which does look to be where q is. Now if we want the area of this triangle, it's half base height. So that's going to be a half of our x value was 3 over 2 and our y value was 3 over e squared. Now if we just times the tops of all three fractions, you're going to get 9, and if we times the bottom, we're going to get 4e squared as required. Cool. Wonderful. Now we've got this general pattern here. So number 2 is what we just did above, and then we got 1 through to 4. Now, with patterns, you want to keep an eye out for like square numbers or things like that. And you might notice there are square numbers up the top. So this number here is 2 squared on the top, 3 squared on the top, 4 squared, and 5 squared. It's always one more than the b value. So the top, so the area is going to be, let's see, I might just give myself a bit more room here. Area, so it's going to be 1 more than b and square it. Now on the bottom, the pattern's hopefully a little bit easier to spot. It is 2, 3, 4, so it's going to be e to the power of b on the bottom there. And the number with the b is just 2b. Sorry, the number with the e is just 2b. 2 times 1, 2 times 2, 2 times 3, 2 times 4. So we can just say the tangent to fb of x equals e to the minus bx at x equals 1 makes a triangle OPQ with area given by that. And b is in R plus. It's got to be a positive real number. Okay, prove your conjecture. So we're going to be looking at this fb of x is e to the minus bx. Now to get the equation of the tangent, it's going to be f dash of a, x take a, plus f of a. That's going to be our tangent equation. So a is going to be 1, because it says up here it's still x equals 1 all the time, the tangent equation. F of a is going to be e to the minus b lots of 1. That's e to the minus b. And f dash of a, or f dash of x, I should say, is going to be minus b e to the minus bx. Therefore, f dash of a is minus b e to the minus b lots of 1, which is minus b e to the minus b. So the tangent equation is going to look like minus b e to the minus b, x take 1, plus e to the minus b. We can do the exact same thing that we did before. So that's going to give us e to the minus b out as a common factor, minus b, lots of x take 1, plus 1. And then that's going to give us e to the minus bx plus b plus 1. And that's e to the b on the bottom, and that's minus bx plus b plus 1 on the top. So that is our tangent equation. So now we can start finding the y-intercept and the x-intercept. So remember, this happened at x is 0. So same process as what we did in part B, really. So y-intercept happens at x equals 0. So y is going to be minus b lots of 0. Well, I should write out the whole equation first. Y is minus bx plus b plus 1 over eb. So it's going to be minus b lots of 0 plus b plus 1 over e to the b, which is b plus 1 over e to the b. X-intercept happens when y is 0. So 0 equals minus bx plus b plus 1 over e to the b. So 0 just has to equal that top of the fraction there, as we discussed before. So bx is b plus 1. Therefore, x is going to be b plus 1 all over b, just like that. So that's our y-intercept and our x-intercept. If we want to draw a little picture of what this looks like, basically, we've got this triangle here. The width of that is going to be b plus 1 over b. So that's the width of that triangle. And the height of that triangle is b plus 1 over e to the b. So that's our triangle there. So we might just separate that out. Area is half base height. It's a bit awkward since there's two b's floating around, but basically that's b plus 1 over b is the base. And b plus 1, I might actually write this out in full, times base times height, so it's less confusing. And b plus 1 over e to the b is the height. So times the tops, you're going to get b plus 1 squared, and times the bottoms, you're going to get 2b eb. Wonderful, we proved it. And this is units squared, since it's an area, and I really should have had units squared there, as required. Discuss what happens as b goes to infinity. So what you can do here is you can actually start just trying a few different values. So you can look at actually, I'll tell you what we can even do. We can graph this as a function. So if we go graph here, and I look at this fraction, it's going to be just x instead of b, but x plus 1 squared. And it's going to look at 2x e to the power of x. Graph that, draw. So if we just go shift trace at 2, I get 0.304 as my area, and that should be 9 over 4e squared, which we can verify. So let's see, 9 over 4e squared. Yeah, cool, 0.304. So the graph is really doing what we expect it to. There it is. Now if we try and plug in bigger numbers, like 5 for the area is getting smaller, 0.024. And if we try and plug in even bigger numbers, like 10 for the area, it's getting very small. So as b goes to infinity, the area goes to 0 from above. The area is getting very small. Now, if you are curious as to why, basically the graph here does get flatter. So that's what it looks like normally. But then the graph eventually gets really flat, and then the triangle gets smaller and smaller area. Yeah, something like that. Have a look on Desmos with sliders if you're curious. It's a good time. All right, there's drawing derivatives questions. So if we've got sign diagrams, and hopefully this is a little bit easier than the conjecture that we just did. E, C, and A are the stationary points. This is going to be x and f dash of x. So downhill before A, uphill, downhill, uphill. Second derivative, we need to put our inflection points, which are B and D. So it's happy, then sad, then happy, or concave up, concave down, concave up. Done. For what values is it concave up? So this is going to be x is less than B, and x is greater than d. So that's the two pluses on the other sign diagram. It's also when we have a happy base shape on the graph. Sketch a possible graph of the derivative. So stationary points become x-intercepts. There, and there. And inflection points become turning points. Now we're sloping down, which means that I'm going to be under the graph, underneath, coming up to that x-intercept. So it should look something like that, coming up towards A. B is going to be a local maximum because I know that it's flat at B. It's a stationary point because I had an inflection point. And I know that I have to come back down to hit that x-intercept there. And then we're sort of going to get a mirror image of that coming up there. Y equals f dash of x. You can also use your little strategy of the graphs. Now, this is true quite often, but not all the time. But quite often the graphs will become less wiggly the further down you go in derivatives. You'll notice that I've got sort of like 1, 2, 3 turning points on f. And then on f dash, I've only got 2 turning points. So f dash is less wiggly. All right, moving on. Okay, next up we have a conjecture again. So we've got x squared log of x, we just need to do that derivative. So we've got the function here. We need to use the product rule. So we're going to have u is x squared, v is log of x, u dash is 2x, and v dash is 1 over x. Be really sure here that you actually say that you're using the product rule since it's a show that question. Very important there. You want to explain all if you're working. We get 2x log of x for that first bit, and we get x squared times 1 over x for that bit. This becomes 2x log of x plus x, and then we can pull out a common factor, and we have what they want. So what I might do here is just write a little description of what I've done in that last bit, factorizing. So if you can put more of these descriptions, that's going to be good because it's a show that question. You want to explain your working and show that it's got a stationary point there. So that is f dash of x. So stationary points are at 0 equals f dash of x. So 0 equals x and 2 log of x plus 1. And it's this last bit that's going to give us that stationary point. So 2 log of x plus 1 equals 0. This is the null factor law. Therefore, 2 log of x is minus 1. Therefore, log of x is minus a half. Therefore, x is e to the minus a half. And since it's a 1 mark question, even though it's a show that, that's pretty good. That's enough working for a mark. Explain why x is 0 is not a stationary point. It looks like f dash of 0 equals 0 because it looks like we would get another one here for x is 0. But f of x is not defined at x is 0. Therefore, x is 0 is not a stationary point. And we can actually verify this by looking at the graph here. Well, the reason it's not defined as well is because you can't do log of 0. In fact, you can't do log of a negative number. And even in the derivative, you'd be trying to do log of 0 there. But let's have a look at what the graph looks like. We've got x squared log of x. All right, so if we just draw that and fix our window, so window standard, we can look at this graph here. It seems to be undefined there. In fact, if I crunch down the window in a really close-up view of that origin, we'll probably see a bit closer what's going on. Yeah, you can see there that it's not. And if I try and trace at 0, I'm going to get an error there. Okay, we've got this here. We can develop a conjecture. So the conjecture is going to look like this. Let fn of x be x to the n log of x. Fn of x has a stationary point at x is e to the minus 1 over n. That's a conjecture there. And then for all n in, well, we're dealing with z with n greater than 2, just like that. Okay, preview conjecture. So fn of x is going to be x to the n log of x. We have to differentiate it again. So stationary point happens at 0 is f dash of x, and we get f dash of x using the product rule. Since it's a proof, it's sort of like a show that question. We have to explain what you're working out is. So product rule, we've got u is going to be x to the n, and v is log of x. V dash then can be 1 over x, and u dash can be nx to the n minus 1. So we've got nx to the n minus 1 log of x plus x to the n times 1 over x. So if we deal with all that, nx to the n minus 1 log of x plus x to the n minus 1. All right, from this point we can pull out a common factor of x to the n take 1. We're left with n log of x plus 1. So this is going to be factorizing. And then that tells us that either x to the n take 1 equals 0, so x is 0. This is not possible as f of x is undefined at x is 0. Or we've got this, n log of x plus 1 is 0. So n log of x is minus 1. So log of x is minus 1 over n. Therefore, x is e to the minus 1 over n. And there we go, we've proved. So probably, therefore, f of x has one stationary point at x is e to the minus 1 over n. And that's really the statement to say we finished proving it. Wonderful. All right, last one, an optimization problem. Show that y is x over root 2. So we can sort of look at this BCF triangle. So there it is. This is y, y, and x. So y squared plus y squared is x squared. That is from Pythagoras. Therefore, 2y squared is x squared. Therefore, y squared is x squared over 2. Therefore, y is x over root 2. Now, technically, that's plus or minus, but y is positive x over root 2 as lengths are positive. So the total area is that. So we need to break it up into, I might just call this area of the triangle and area of the rectangle. Just use that little shorthand. Area of the rectangle is quite straightforward. It's x with 10, well, since it's show that, length, well, I'm going to go width times length, which is x and 10 take x. All right, good. We might work with that later. Area of the triangle is going to be half times base times height. So that's going to be half. Yeah, this triangle is a little bit funky, and this is what can be tricky with this question. The base and the height of that triangle on the top are actually both y. And that's if you arrange it so that B is sitting there, C and F are sitting there. So it's actually y and y. You've got to be very careful with that. The base of the triangle, I mean, technically we could use the base across the base, but we don't know what the height of the triangle is in that context. Whereas we do if we sort of flip the triangle around, know that y is the base and y is the height. So this is going to be a half x over root 2 is y, and x over root 2 is y from A. So this is going to be x squared over 2 times 2 on the bottom. So it's x squared over 4. Let's see. I think this is probably worth expanding. So that's 10x take x squared there. So therefore, total area is going to be 10x take x squared. Well, actually, I might write it like this. Area of the rectangle plus area of the triangle, which is 10x take x squared plus x squared over 4 which collecting like terms gives you 10x take 3/4 of x squared as required. Beautiful. Find the value which maximizes that. Area is 10x take 3/4 of x squared. dA over dx, so that's the derivative of the area. It's going to be 10 take 3/2 of x, because I've doubled it, so it'll go to halves rather than quarters. Check that on a calculator if you want. So therefore 0 is dA dx. Therefore 0 is 10 take 3/2 x. Therefore 3/2 of x is 10. Therefore x is 10 times 2 over 3. So x roughly equals 6.67 centimeters, or a 6.6 recurring if you want. There it is. So we need to sketch a picture of this thing. So 6.67 centimeters. By the way, you probably should make sure that this is a maximum. You can do that a few different ways. You can check all the endpoints, or since we're going to need it graphed anyway in a second, I might graph this now. Let's see. So the area function was 10x take 3 over 4x squared. Draw that. There it is. And we can see that g solve max should happen at 6.6, which it does. By the way, this solves the last question here, which is that the area maximum is 33.3 centimeters squared. You can give an exact, or you can give... So both are fine. One thing that I will point out, you might notice that I've been giving all my answers in this to 3 significant figures, and that's because I've asked you to at the start. SACE is very keen on that too. So that's why you'll notice 3 significant figures everywhere. One last thing we need to do is just draw this. So if this is 10 take x, this will be 3.33 centimeters, and that's going to be 10 take x. Now we probably should figure out what y is as well in this diagram. Y is x over root 2. So if I take the x value, use the full version, not the truncated version, root 2. There it is, 4.714. So 4.714 centimeters, 4.714 centimeters, just like that. And I guess we could have, yeah, I guess I'll label the other way, 3.33 centimeters, and we'll whack a right angle on there too. So that's probably everything you need on that question there. And we're done.